Okay, so you can see all this stuff here. It's like this. Tonight it will be like in two parts. Like we decided to have a first small talk, a seminar. We also you saw in the program that there is a part that is called workshop that is possible to do if you brought your computer. If you didn't, I can still show you some few things. Did anyone bring a computer? Yes. Did anyone install SuperCollider? Oh, nice. Okay, great. So we don't have much time on the workshop, but we tried some exercises, and I can at least give you the bit of code that will allow you to do some sonification, and you will be able then to play around home and at parties to impress all your friends. You will see. First of all, thank you, Sergey, for the invitation. We know each other for quite a long time now. He came to visit our small independent cinema with Ruslana, with this very nice exhibition called Gravitron. Do you remember this exhibition? Yes. It was all about. We really loved it because our cinema is called Cinema Sputnik, and it was really like about all this imaginary that we are like super dreaming there on the western part of Europe. Like for us, it's like really all those people like really fantasize this old technical, scientific, Sovietic era of the 70s, like the conquest of the space. So he came with this. We then visited two years ago with our super project with TVs, and I don't know if anyone was there. It was all about analog, not even electronics, but electric music. We brought a whole laboratory. It was back then in this very nice space called VCRC that is not anymore, but that is still alive in our hearts or whatever.
VCRC is still alive.
Yes.
The place is
yeah, the place. Yes, sorry. It's only a physical space, but the spirit is still there, of course. So thank you for the invitation. I'll be talking a little bit, as the title says, on data sonification and its broad interpretation in science and art. It all started with discussion I had with a friend, physicist friend from CERN, because Geneva is very close to CERN. I myself, or maybe I didn't introduce myself. I will start with that. My name is Daniel Siemaszko. I'm engineer, but I also do music. I also curate films in independent cinema, and I did work at CERN also as an engineer. There I could encounter some physicists or other technicians, other engineers, among which Dr. James Beham, who also is a fan of cinema, so we talk about a lot of stuff but science. And at some point, after one beer or two, we decided to talk about this big trend. What is it? What they all talk about? Data, sonification, how to make art with science or science with art or whatever. How this all mixed up? How can you take some data and make them speak? So we were kind of skeptic about this whole idea. We thought that maybe it's all about our own subjectivity. So we started talking, discussing, trying out. He did some sonification with some CERN data. I did some sonification with some others. And we put together this presentation that I already presented once. It was in the symposium for spatial sound art, talking about how do science and art come together, or move together, or don't cross at all. This is one of the very subjective questions that will be asked at the end of this presentation. So with him, we after all those discussions, we decided to put down a paper that was specifically talking about science and art. But talking recently with Sergey and I saw like the thematics of this biennale. I tried to think about how this in art practice and science practice could be also referred to what we call the big data. The big data, we are in it. Like it's not new that we have servers full of data, but what is new now is our access to it. So now everything is accessible, and all the data that you put is also accessible to a lot of people. So this raises a lot of questions, and what is interesting in this research, artistic or like aesthetic research, let's say, is how, artistically speaking, people did use those data in order to put it, to say something, to make a statement. We will see that there are several statements, and we see what they mean or don't mean anyway. And of course, the big question nowadays is also data surveillance and cyber security. So I will not be talking about cyber security, but we will see how some people did use it in an artistic way to make another kind of statement. I remember on Friday, like we were talking about activism in art, about how some people may be activists or not, like by doing art, like how are they activating people. We will see that maybe somehow, even though it is not intended, maybe it still activates some things in our minds. It brings back like memories, or for instance, for example, it brings some fears. If we talk about big data, I put some sound, I tell you, yeah, I found it in the dark web. Put down the light, it will give you this this atmosphere of fear. So this is what I will be talking about during this presentation. Okay. So yes, first question: what is data sonification, and how does it bring together science and art? Maybe as a first parallel, we could talk about visualization. Like we have plenty of ways for visualization of data. Let's say you see those curves, economic curves. It goes down, means it's catastrophe. It goes up. Like you have the feeling that okay, everything is good. Like economic growth and everything. You see those curves going up and down, and you kind of don't need to read them to have already conscious of what they mean. So there was a big question among several research topics. Like, is it possible to use sonification of data in a practical way, not only artistic way? Let's put some music and okay, I take some numbers. We listen to music and I tell you it's this, but in a really practical way. So this data come to a set of algorithms that put them together, some sounds with some parameters, and in fact, instead of like if you are like checking some data and you're looking for something, instead of visualizing the pattern, you will hear them. And maybe some people say that our auditory capability is far superior than our eye capability to recognize patterns, rhythms, or dissonance, whereas the eye could maybe not see them. So a big part of research is going into that direction. Very simple example of sonification would be, let's say, metro gate, would be your microwave. It's all those elements that give an information through sounds instead of a visual alarm. There is a sound, and instantly you know what it means. You know that your ticket is valid or not. You know that your food is ready in the microwave. etc., etc. So this is the practical part of data sonification. What about art? Is it possible to bring the meaning of data, so the meaning of an interpretation of data into artistic practice, and bring the message that would be supposed to bring the data? This is one of the big parallels that we found while speaking with my physicist friend, that at the end it's all about interpretation. When you have a set of data, let's say you make an experiment, a huge experiment of a lot of data, and you're looking for something in particular, you have an idea of what you want, and you will go straight to where you are looking for it. So you have an idea of what you're looking for, and you have an idea of how the data is organized, so you will go deep into that. Parallel with art, if I tell you, okay, I sonified the data of a result of CERN research, or whatever, you already have an expectation. You expect some kind of sci-fi movie sounds, or some kind of noise, like something that will take you to a kind of atmosphere, that take you down to some kind of atmosphere. If you don't get this, you might be disappointed. If you get this, you will be like, yes, I hear science. This image, I think it comes from an album by Kate Bush called Pi. In her song, there is a complex melodic pattern that is taken straight from the decimals of pi. This brings a kind of atmosphere in the music. You have something that takes you somewhere. I believe that this song does not make talk the number pi. I believe that it's the idea that you have, that it talks about pi, that you feel like, oh, okay, we are getting closer to something mathematic, so natural or whatever. Or maybe what you can understand, what Kate Bush can take you is like an idea of like how big this number is, or how deep research in mathematics is. But it's not this number, pi, that will be speaking directly to you. I mean, no offense, I'm not talking about whether it's bad or not, but like it's really about what it means and how we can put things together. So this is basically the point that I will have all through this presentation, is about what we expect, is about how do we want to interpret things, and what is our knowledge about what we will see, and how difficult it is to simply come with something raw, unexpected, and read it as something that, just like scientific data, if you take raw numbers and you don't know how they were taken, whatever, it will anyway mean nothing. So whether you sonify it, or you read it, or you make some art with it, or some science with it, it will not mean anything anyway. So this is the big parallel that we found about science and art, is that in each other's practice, we are expecting something, we have some knowledge, and we also try to meet people's expectation, because it's all about communication at the end. I have some interesting sonification examples. The first one that maybe you all know is like, you've been maybe on YouTube, you can find, or maybe you can go tonight for sleeping, it's really nice, very atmospheric music. Check the music of Jupiter or Saturn or Moon or whatever. It's like a huge data bank of sonified planets, stars, satellites. NASA was doing it, like taking measurements, electromagnetic measurements, doing a kind of like, as you can see here, maybe you can see you have time, the time domain, and the frequency domain. We have here, in this case, this is the Cassini case. It was recorded with some electromagnetic measurement, and it was the activity of the plasma inside whatever. I don't know what parameters they choose exactly, but what's important is that they made a mapping between one result and something that one can hear. One can hear something about between, so to say, 20 to 15 kilohertz. Electromagnetic fields is far above megahertz. So anyway, we cannot hear it. And anyway, in space, one cannot hear anything because sound is a propagation of pressure. And without atmosphere, there is no sound propagation. So anyway, we cannot say that a planet is singing or whatever, but maybe we can. So anyway, this is and also one of the first sonification I ever heard without knowing what it was quite a long time ago. I came across this. Did you hear about this satellite that landed on this comet called Rosetta? And there were, maybe you heard of it or not, but scientists, like, they went through some electromagnetic measurements. They did this mapping they do usually for planets and whatever, and they were mesmerized by the fact that they had the feeling that the comet was singing. Let's hear it. It should work. It's quite striking because it does have some kind of soul feeling. We have a feeling that it has something to communicate. Maybe. Does it mean that every single comet has its own way of singing or way of it has the same electromagnetic signature that we can maybe recognize? So is it possible that, like, we have a rain of comets and then we can, like, just listen to everything and say, oh yeah, here is a cousin of Rosetta, most likely, because it has a kind of electromagnetic response due to its composition, to its shape, to whatever. So that was the first example I wanted you to hear. About science, still, like, one of the very first obvious thematic that one tried to sonify is, of course, DNA sequence. Maybe you know this book, Gödel, Escher and Bach by Douglas Hofstadter. He wrote it like quite a long time ago, 30 or even 40 years ago. And it's quite a good book that makes all sorts of parallel between science, music, composition. One of the chapters was dedicated to DNA music. So what is it exactly? So So DNA sequence has a sequence of 4 letters or 4 entities that we can map somehow into a series of pitch, note, whatever. So a lot of people did this. Does it actually mean anything? Does it actually mean that you can hear the DNA of someone or something? Or can you maybe recognize it? I would say maybe, maybe not. But anyway, if you read this series of letters, can you anyway recognize it by looking at it? So maybe listening to it is fine as well. There was an example by, this is very artistic example, Carl Michael von Hauswolf, Swedish composer, experimental musician, did recently, it was actually in Poland this summer, at Sanatorium Dźwięku. He did a piece called Data Sonification of HIV DNA. So maybe let's listen to it first and let's make a comment later. Where's my mouse? Oh. My first question when listening to this was, what if it did put some random series of numbers, or maybe the DNA of a no kid that has not such a heavy tension in the word HIV? Would this have sounded the same or not? Here it's a striking example about how the intention comes first rather than the real content. Because I am sure that he could have put a random series of 4 sequences, and the intensity of this music, the depth of the meaning that he wants to put into it is still there, because it comes from the fact that he announces that I took HIV and I sonified it. So there is already an expectation of something quite deep and heavy. Another artist and scientist called Carla Scaletti made some very, very interesting research, because actually she is both a scientist and a musician. As a scientist, she goes deep into the sonification, the use of sonification for practical matter or for scientific research, for scanning data. Instead of using the eye, she wants to use the ear, because with the ear you can really notice the very subtle differences between one set of data to another, and you go like this. She made some work also at CERN, and funnily enough, she started work with a choreographer. So she used the same sounds that she produced as a practical matter, and she put it down, turned it down to music for a choreography that was supposed to talk about atoms, particles meeting together, colliding. It was talking about all those scientific words that are very present at CERN. Elementary particles, particle physics. So that was very interesting, because she used maybe you want to hear that, because actually it's very nice. Now, the only thing is that videos are not working so well. Let me. Yes, here we come a bit closer to what we could have expected when we talk about particle physics and sound. This kind of like very strange sound coming, like surrounding you, with a deep bass somehow going very slow, like showing like the ungraspable aspect of what those physicists are dealing with. So that's when meeting Karaskariti, that's when I first encountered the idea that data or things can also be sonified and not only visualized, and that can actually be much more powerful than showing just some graphs that do not mean much more anyway. Very quickly. Oops. Yes, sorry. Just very quickly, this was an example I came across that was very funny because it also had how to bring science to art. There was a work, like very recent work by some scientists that were talking about quantum music and subjective interpretation and entanglement. So quantum music, I don't know how to, or maybe you will hear it later at the performance. It's like, as you know, like quantum states, there are several quantum states that as long as you don't observe them, they can have all those states at once. So basically they state that it is possible to, in terms of music, put down a pitch and like everybody will have its own interpretation. So it goes back to like your own subjective interpretation of how you perceive a pitch or how you perceive a music. They also say maybe someday in some future with entanglement we can hear actually what is going on at the other end of the galaxy, as long as we have two entangled particles and that we can sonify the particle. That goes a bit far to me, that's a bit science fiction to me, but it's still very interesting to see that how like all those elements. By the way, quantum physics has a lot of parallels, not only in music, but some people also use it to explain some phenomenon in social science, for instance, or any other like biological phenomenon. So this is also one of the fields where we can apply any kind of physics. In this case, quantum physics. Another one that looks quite science fiction, but is very real, that one. I don't know if you can see the red one, it's a globe. This is so-called 3D sound, real 3D sound with 130 speakers. In this project, this is in Virginia Tech, they recreated a globe, a sonic globe, supposed that is supposed to recreate the state of the atmosphere of half of the globe. I guess you can turn the globe upside down and you will have the other half. In this way, it is really used not as art but as a science. So scientists can come in the middle of the globe, in that way can observe all the different parameters changing and evolving in Earth atmosphere. So being able to, instead of seeing climate changes, more atmospheric changes, pressure, instead of seeing them, you can hear them. With 130 speakers, so it has like a technicality that goes like far beyond the capability of one person only. It's like how to recreate this sonic sphere, where really for this one person that will be in the middle, to being able to visualize, in fact, instead of visualizing, to hear the state of Earth atmosphere. So maybe this will come, this is still at the state of research, but maybe one day it will come it will come to a extent that it will more wider spread, that we will be hearing data instead of visualizing them. Did you see already like some graphs, and like you go through graphs and it's like no, boring. You lose your attention. Maybe with sound it will be better. So this was about like high physics, high energy physics, big data. I have two more examples that I really like. This is also a scientist and an artist called Lindsay from Milano, Italy, and she does sound design, she does art installation, and she does research also. In this case, she made a work called Disclosing Cyber Attacks on Water Distribution Systems. This looks a bit funny, but that's why I really like this this idea, because this is one of the very safe topic where we can talk about cyber attacks and how we need to protect them. It is all about the water distribution system in Singapore, I think, on which she worked for 6 months. And there was, like, the main issue was that operators of the water system were sometimes hearing alarms, ringing alarms that is supposed to mean something, that something is dysfunctioning or that there is some attack or whatever, and they got so bored by this very stupid alarm, like meow, that they just disabled it, and therefore they were unable to hear or sense a case, unlikely case, but still possible, of a cyber attack in the water distribution system. So this was a way for her to come to a very practical question in this course, and how to bring the variety or the complexity of attacks or problems that can come in a sewer of a distribution system, and to bring it to sound in a way that the operators can decide by what they hear whether it is serious or not. So for this we will hear two examples. She made first background sound that is typical of what one could hear in a sewer, but with only synthesized sounds that do reproduce with the data that comes from the whole distribution system from Singapore. Let's listen to this background. I quite like this. I don't know if you ever went to a water distribution system or to any other industrial site where they are dealing with a lot of systems and sewers and machines. I would say that's a very typical sound that we can hear, a very typical atmosphere that we have, like machines there, like big echo because like we have huge holes and like a lot of things happening. So this sonification is illustrating a normal situation. So now there is a cyber attack, and we will hear the difference will not come from the fact that we notice there is a cyber attack, but we notice that there is something dysfunctioning because it is different. We will see what she came out with. So it's quite different, and the way it is done is that any kind of small difference in the parameters that we are sonifying or using from the data in the sonification, meaning if you have a set of 10 parameters, maybe one is the pitch, the other maybe is the decay, maybe the other one is the color of it or the attack of it, whatever. If those parameters like change a little bit, we will hear a small difference in the sound that we hear. If there's a big difference, we will hear, as we did here, like in case of a cyber attack and everything goes down, we have a very different experience, sonic experience of what the operators are experiencing. So, to me, very subjectively, it sounds like a very interesting way of sensing a whole system that you are supposed to be watching over. After this research, unfortunately, I think she proposed a system, and it was not yet accepted because the managers of this distribution system were not entirely yet convinced that it's a way, but it is still going because more and more people, more and more artists, more and more scientists are really thinking about this way of coming into visualization or surveillance. This is this is how I wanted to approach cyber attack in a much nicer way than what we would have expected. When we hear cyber attack, we think about privacy, and we think about how we are not anymore master of our own image, and this makes a very good transition to the very last example that I wanted to mention in this introduction. Is the work of an artist, of a Chinese artist called Shu Bing, called Dragonfly Eyes 2017, which is actually visual and sound work. It's a film on which he used publicly available data from surveillance cameras, and this is quite interesting. And this really comes to as an argument to Friday's presentation, because Shubing, with his work, is absolutely not talking at all about surveillance. It's not absolutely talking about the morality of the fact that there are now cameras all throughout China that are able to recognize your face, your car, your movements, and like put all this data together and make assumptions and decisions, and no, not decisions yet, not that I know of anyway. It's a story of an entity that has 28,000 eyes. It's called Dragonfly, and it's simply watching people. In his film, it's a simple fiction that is quite simple and has nothing harmful and nothing tension to it. It's a very simple story. But the setup, the whole setup, knowing that all the images that you will see are taken actually from real surveillance cameras made publicly available, so like anyone can check it, can see it and take it and do whatever he wants with it. So there's no needed words in saying what it is doing. Like the film says it's all. This is the situation. Maybe we can watch. I found a trailer. It is very talkative and I like it very much. Let's see if I can. Yes, it's about 2 minutes 30. I really like it. I really wanted to show. I would have loved to show you the full film, but maybe you can find it somewhere else. Okay.
This is Dragonfly. Dragonfly has 28,000 eyes, blinking 40,000 times per second. Hour by hour, checking. Second by second, deleting. Searching, identifying. Scenes, laws, characters. This is rare. Zero 100 times each day. This is a woman. Her privacy is all used up. And on the lead.
听，你知道这是哪儿吗？
我在一张床上，有人跟我说要我安心睡。
我也在一张床上，有人按住我，有人打我，要我一觉不醒。
That was just a trailer. The film is about 70 minutes, and I come to it. Like, it would have been a fantastic film to illustrate Black Cloud, artificial intelligence, big data, and in the post-Chernobyl era. Maybe you can find it. I hope you had time to check the reference. Okay, yeah, the reference is here. You can have it. No, as I was mentioning, like, the way that all those videos are put together, the way the story is built in the film, like this entity is starting imagining things, like inventing stories. It's a very, in a very naive way, and very, like, so to say, safe way, because it's only observing. It really raises all those questions, like all those fears that we are brought to when we are seeing all this unknown of how things are evolving now with our data, with all the questions that we like here in Europe. We still have a kind of illusion that we are still kind of choosing what we put on the net, on the data, and what can be used. Like in China, there is no more illusion, because they, at least they go honestly, they say no, there is no privacy. Here we still have a kind of sense of it, but is it true or not? I don't know. This is you to decide. But there's also this question, like, that all those eyes through cameras, and all those ears through microphones that can be either put artificially, or that we are all anyway carrying. Like, I'm sure, like, more than half of this audience has a camera and a microphone in his pocket, and that the phone is open, I mean, is on. And how do you know that this conference now is not recorded, let's say 50 times through 50 different ears? This, no one knows. So this question of the big data and sonification was this part that I wanted to add in this seminar. And maybe you will be still interested in having, like, this one example that is a bit more nicer and a bit less scary, where in fact the big data was invented. It's oops. Yes, CERN, Geneva. Yes, this is where I had the chance to work a little bit. They say it's the inventor of the World Wide Web, which brings us to the way that we have now to access the big data, and also to feed the big data with our own data, the World Wide Web, which at the beginning was used in a very noble way, with a noble intention, only to share scientific result, and also to share the machines to calculate, to share the calculating force for dealing with all the data that is coming. How much? Petabillions of data every year. It's like, if you burn all the data collected at CERN in 1 year and you put it in Blu-rays and you pile it up, you reach the moon. It's something like you cannot even imagine. Like, so all those data are there and like collected, and like so it's impossible to scan it all. It's impossible. It's impossible to have a very objective way of what's going on. As I said at the beginning of this seminar, there is a need for an intention. There is an intention in this set of data. The intention recently was to find the Higgs boson, and there was a kind of an idea of where they would find it. So they discard all the rest and they go and find this. They go and see what they want to see, as most of people hear what they want to hear. And in this, of course, environment, if you type CERN sonification, there are plenty of examples. I have some people from Birmingham called the Birmingham Electroacoustic Ensemble that did some sonification of real experimental data. Here, on the left-hand side, you see this cone. This is the decay of a Higgs boson, and every single parameter has been put to a pitch, to an envelope, to an attack, to a decay, to whatever, so we can hear a sound. So some people did some, but honestly, like all those things, like they look more artistic than really usable. Even though Carla Scaletti that I showed before, like really used it and actually did manage to find a way to scan through data that has actually physical meaning. And what you see here, that was for the 60th anniversary of CERN. They did a big symphonic concert with sonification. Sonification of an LHC experiment. So we can see there is a flute and a clarinet. There are plenty of other instruments with some data, parameters, and you then add, so each parameter is an instrument and it has a pitch, whatever. This is also a way of sonification. Does it has practical meaning? I'm not sure about this. So if we come to data, maybe you recognize this is a detector. Does everybody know, does anyone not know what is done about at CERN? CERN. Yeah, okay. So yeah. So you have particles, no?
But maybe you can explain it.
Okay. Okay. Yeah. So in order to find answers about particle physics that physicists are having for now years and years, because like with the so-called Higgs boson that we found, that is supposed to explain why particles or you have mass. This theory was already thought of like in the 60s, but there was no way, absolutely no way to verify it experimentally. So we had to build like huge machine, 27 kilometers long, put down particles to make them circulate at the almost speed of light and make them collide so they break. And what do physicists actually analyze is what's inside. It's like the behavior of all the debris from the collision that is going and hitting the detector that we see here. A very good analogy is like when you are a kid and you have this little car and you want absolutely to know what's inside. You take a hammer and you smash it. That's exactly what is done at CERN. So every detector is giving massive amount of data to huge data centers that were existing even before Google was born. They were the first data centers like dealing with massive amount of data. They were the first data scientists anyway, all working for the purpose of finding some, what we could say, truth about physics. So my friend, that's when my friend James Beham come, because he did some sonification with this. He said, because he's really deep into that, he's researching about a multiverse. Multiverse is like, it comes to quantum physics. Multiverse is, literally speaking, a parallel universe. It's like, so there are many parallel universes. Like right now, like there are many like copies of ourselves, like having the same situation with some differences and everything. And he's really researching that in a very serious way. And he's also looking for the so-called gravitron, which is the equivalent of the electron for electricity, but the gravitron is its equivalent for gravity. Gravity is still a big mystery. Why gravity? No one knows yet. Maybe they have some clues. So he did some, like he used his data that he knows very well. He picked some 6 parameters. He showed here, this is one example of what one could do, but he didn't do that at all because it was a bit boring. He took 6 parameters and he, as I mentioned before, he matched them into like sound parameters that in a synthesis we could call, I repeat them all over again, but like duration, envelope, attack, decay, pitch, volume, of course. And the idea is that, unfortunately they didn't do it with the SuperCollider but with Python, that if you have like those results, this is the representation of the 6 parameters that he has from, let's say, one experiment. He can scan through several experiments, and when he finds an interesting event, as you can see, already visually is striking how different the upper line is from the lower line, it will sound different. So he did this like more for fun, knowing that it will not really make a breakthrough in data sonification, but what we can hear now, because he did also, this is my friend James, maybe you saw him giving a TED talk about, maybe about astrology and astronomy and cosmology, maybe, He's quite well known, in fact. And he was giving a conference, and they took him at the end of the conference. They told him, hey, we want to hear your data sonification, and they did a kind of noise improvisation with data sonification and guitar. This is not what we will hear, but we will hear to a very funny way of putting together experimental data that show Gravitron, and that is about finding the truth of in scientific theories in a way that actually I don't think you would expect. Let's hear it. So this is no sci-fi, this is no like big through, this is no like very strange sound that will put you to a hypnosis that will make you understand the physics. But we heard it all, Higgs boson, Gravitron, everything was there. This example like really comes into to showing like how important is what we expect from what people will present you, whether it is science or art. It shows that the implication of also of what we want to show and how we want to meet our first impression, like that we would have of something that someone will talk to you about, or like show you or present you in an art exhibition or like in a science conference. So bringing these two together like shows how in fact insignificant it is really to use in an artistic way sonification of real data to kind of illustrate something, because we already know what we want to hear. So this came to a big question, in fact. We have all those hard drives, we have all those files, all those servers, like full of different type of files, JPEGs, PDFs, MP3, MOV files. And what if there's a kind of catastrophe and in 100 years some archeologists will try to look through our data and read it? This was the case then, like the Europeans couldn't like decipher Egyptian hieroglyphs until they found the Rosetta Stone that was giving a hint to better understand what they were meaning. Is there a Rosetta Stone for JPEG or PDF files? All our documents are now in that kind of formats. And if you don't have a PDF reader, what does it mean? What is this data? The series of numbers. It will be numbers, just like a DNA sequence. If you don't know how to go through, if you don't know how to interpret it, it will just sound like noise or just a random series of pictures. This is one of my most interesting reflection now. That do you know that maybe most our first hard drive are maybe now 10 years old. Do you know the lifetime of a hard drive? It's 10 years. So it's now we will start experiencing a kind of digital amnesia coming slowly. The data that is not actively kept will disappear, or just stay as a bunch of one and zeros, but with some holes in it that makes it unreadable with our classic PDF reader, for example. It's the first time that we can kind of realize that all this big data that we talk about is kind of very, very fragile. That if I remove the plug of a server, how many pictures and how many whatever that you have stored there will maybe disappear. But doesn't matter really, I don't know. A lot of libraries burned, like Alexandria. There was a case in South America when the Spanish came and burned down all the writings. It was all happening in a much longer period of time. I didn't check the reference, but I believe that some data already was lost totally. It was at the fall of the Soviet Union. I don't have the reference. If anyone heard about it, maybe we can discuss about it. But there were some information was stored digitally in magnetic bands. I think I don't know. Something was stored. Some information was stored, and it came to a point where some information was stored only digitally. That could only be read by a computer. And after the fall of the Soviet Union, no one kept this. And when scientists came back, or historians came back to those computers, it was unreadable. So it happened already, in fact. I have no answer. It was only questions. Only questions. Is there a Rosetta Stone for digital data? About 100 years ago, a poet, Austrian poet called Rainer Maria Rilke, did an experiment. He also wrote an essay called Primal Sound in 1919. It was 100 years ago. He wanted to use the needle of an LP, of a gramophone, on the skull of dead people, and hear if one can hear their soul, if to see if the skull has the memory of the person that was living inside this body. It's a poetic question. One thing is for sure, that every skull will sound different, just as anyone here is different. But will we be able to really get the essence of the person that we are, with whose skull we are listening to? I believe that archaeologists in 100 years will have the same thing with listening to our data. They will be reading our data without any idea of what it's supposed to mean, without any preconception, without any expectation. So what will they hear? Just a series of 1 and zeros. This is a last example that I wanted to put, because this also concluded my discussion with my physicist friend. So if there is so much expectation, so much interpretation, so much things that you know, so much knowledge before coming into use of data, whether it is art, of science, so how can you plunge into kind of information and data without knowing nothing? What will we hear? I guess you know what we will hear. But let's hear it again. So that was the sonification of results from Atlas, but it could have been an image, it could have been the song of a comet, it could have been your PDF file. It will all sound like this. But there are differences. Maybe in this we can hear or not. Anyway, this image is the byte map of the file that I used. So you can see the 1 and 0s. With this white noise, it's not exactly white noise, but with this noise I want to conclude this talk, and before we go to the second part, small part, which is like where I will show you how you can do some sonification at home with your own computer. I don't know if there are maybe questions or like things like someone wants to react to before I go and move with the workshop and we move with the performance that everybody is expecting anyway.
I think for this Italian musician, Sarah, I don't remember his name.
Lindsay, yeah.
I don't know in which format she presented her musical work, but I think it was just probably the way she should do it like lighter for ears, because if people will hear it for a long time, they should just
Yes, of course.
just to say it's a really nice thing.
Yeah. I don't know her personally. I came across her work through scientific papers where she was describing what she did exactly for this sonification. But yes, you're right. There's a way of how you put it. That's for sure. Yeah. So there was in the program there was like a seminar and a workshop where I can show you, like there are two ways of doing it, and like everyone can do it. I was suggesting how to do it like with a program called SuperCollider. SuperCollider is a software that allows to do some programming and to do basically whatever you want, but it's really sound oriented. And there's another way that people that do not want to program or really are afraid of programming, whatever, there is this thing I found. I think it's Google. It's called two-tone. This you can. I don't know if it works in your phone, but it's basically exactly the same thing as we will do with SuperCollider. You upload a set of data. CSV file, is typically a set of numbers. And then you can change whatever you want, pitch, length, whatever, and then you can hear your data in a very simplistic way. If I go back, so this method, it's a super easy method that I know that some people brought their computer. I don't know if maybe you want to put them down, or maybe you can see a little bit. There will be a break before the performance anyway. How I can give you the file, but let's. Wait. Yes. SuperCollider looks a bit like this. There's a window here. Don't worry, I will put it wider. And I did a small, it's quite striking how it works. And wait. And I'm sure that even people who do not understand programming will understand what I do. Basically, so it's a server that I am running. There is a synthesizer. It could be like this, that can take several parameters, such as it's okay, don't worry. Decay, frequency, attack, envelope. So I load it to my server. Then I have a file. I have a file that is called sonification.csv. I will show you how it looks like. It's a simple set of numbers that what you can see in Excel, for example. I have 5 columns of data. It could be anything. It could be some market trends. It could be your own measurement in a chemistry laboratory. It could be some electronic measurements, wherever. And let's say you have 5 columns or 6 or 3 or whatever. In this case, I was working on smart grids. So we will hear the sound of smart grids. Did you ever hear of this new word, smart grid, that is how to put artificial intelligence in the way of distributing electric energy? This will come soon, anyway, because this is the only way to integrate solar panels, for example. So we will hear in this case the sound of smart grids, but you can put whatever you want. You can put some numbers such as the age of all the people that you met today. It can be whatever that has a meaning or not to you. All you need is to have a list of numbers. So I load it. We see, so I have all those numbers, and then in this way, here there is a way of like, there's the first part of my own subjective choice. It's how I do assign a column of numbers to a parameter, such as frequency, decay, attack, or whatever. So I have some frequency, some level, some attack, some decay, some duration, and it all corresponds to one of the columns. Let's put it. There is a part of linearization, and this is one way of playing it, this is one way of playing it, this is another way of playing it. Or maybe let's listen to this first one. This is the first that I do. I don't know, it will hear like this. And there's another one. Oh shit. I have a little problem. That's it, yeah. I can do all the changes I want, as long as if you understand well that I use one set of data that I put to one parameters in one synthesizers, for example, where you can come and see on my table there is a Doppler synthesizer where there are many kind of parameters, but you take them analog. In this way, you take it digitally in a sequence that I decided also very subjectively, exactly as I would decide. Thank you. Exactly as I would decide how to represent visually a set of data. So that's it. For those people who I went quite fast because, but I will give you this set of code, and we can even before or after the performance try out quickly on your computer and see if it works, as long as if you have a set of data, a small set of Excel sheet with 2 or 3 or 4 parameters. Okay, that's it. Thank you. Yeah, I really like this piece of code.
So how do we try it? We try it here, like directly from our seat here? Or
Yes, I can sit here for a moment. There is a break anyway, because we'll set up. We are almost ready for the performance. We decided to play. We will play. Let's say, what time is it? 8:45 is okay? Yes? Yeah. So those people who want to have a beer or a cigarette can go, or the others that want to try out the code can sit here at their computer.